Okay, let's dive right into this explainer, shall we? We are trying to unravel, literally, the ultimate mystery here: how our local planetary neighborhood, and honestly, the entire universe, actually came to be. It is the greatest detective story ever told. We're talking billions of years, unimaginable distances, and today we're going to walk through the evidence step by step. I mean, how did all of this get here, right? It's a question every single one of us has asked while staring up at a starry night sky. We are going to explore this grand question by starting out with some early, kind of flawed scientific guesses about our own solar system. And eventually, we'll zoom way out to the mind-bending realities of the Big Bang and these invisible cosmic ghosts that shape our reality today. All right, Chapter 1, The Local Neighborhood Mystery. So, let's start small. Well, relatively speaking anyway. We're looking at how our own solar system formed. You've got early thinkers, guys like Immanuel Kant and Pierre-Simon Laplace, who basically looked up and thought everything kicked off from a massive, beautiful, swirling cloud of gas and dust, what we call a nebula. Now, these two pioneering thinkers actually had slightly different takes on this whole nebula idea. Kant had his gaseous hypothesis. He figured cold particles out in deep space were just constantly crashing into each other, and those collisions whipped up heat and eventually formed a spinning nebula. But then Laplace, in 1796, counters with his nebular hypothesis. He was like, no, wait, there was already a huge, hot, spinning nebula out there, and as it radiated heat and cooled down, it shrank, spun even faster, and just chucked off rings of material that eventually cooled to form the planets. But here's the catch, and it's a big one. Both of these theories had absolutely massive plot holes. I mean, science is all about testing ideas, right? And these just did not hold up to scrutiny. Kant couldn't tell you where that initial matter or energy even came from. Plus, his idea totally broke the laws of motion. Particles just randomly bumping together don't magically create a sustained spinning system. And Laplace had issues too. He never explained where his giant hot nebula originated, and honestly, his math just didn't work. If he was right, our sun would literally be spinning at a phenomenally high speed today. And, well, it isn't. So scientists had to keep guessing. And that brings us to the tidal theory, which is way more dramatic, honestly. It suggested that a massive star just kind of flew incredibly close to our young, newly formed sun. And the sheer gravitational pull caused these huge tidal bulges, literally ripping spiral arms of material right off the sun. As that star zoomed away, that ejected stuff got left behind in orbit, eventually cooling down into little planetesimals, then full-blown planets, with comets and asteroids left over as, cosmic debris. Moving on to Chapter 2, the accretion solution. Since those earlier theories were full of holes, scientists had to go back to the drawing board. And in the mid-20th century, thinkers like Otto Schmidt and Viktor Safronov had a massive breakthrough. They came up with the accretion model. Instead of dramatic star flybys or giant rings being thrown off, they proposed this brilliantly simple step-by-step progression where matter just clumps together. It goes from a nebula to tiny dust grains, then boulders, then larger chunks called planetesimals, and finally, boom, planets. It's all about constant accretion, just particles sticking together over unimaginable stretches of time. You have swirling gas and dust that gradually bind together. The tiny grains become little boulders, those smash together into planetesimals, and gravity just keeps acting like a cosmic vacuum cleaner. It sweeps the orbital lanes clear, building up the familiar planets we actually live on today. All right, Chapter 3, zooming out to the ultimate mystery. Okay, so we've kind of figured out our own local solar system, but let's zoom way, way out. How did the entire universe itself form? This is where the Big Bang hypothesis comes in. Georges Lemaitre proposed this back in the 1920s, and it totally flipped our understanding of reality upside down. He theorized that literally all the matter in the universe used to be crammed into a single insanely dense primordial atom. Then, a violently massive explosion happened, scattering all this dense matter and dust everywhere. And over millions of years, gravity slowly pulled the denser pockets of dust together to form the gas clouds, the stars, and the massive galaxies we see tonight. Which brings us to Chapter 4, Finding the Cosmic Fingerprints. Now, you can't just drop a grand theory like a cosmic explosion without some serious proof, right? Luckily, the scientific community found the fingerprints they needed. The legendary Edwin Hubble gave us our first major clue with something called redshift. He noticed that distant galaxies are literally speeding away from us in every direction. And because they're moving away, the light waves they emit are getting stretched out, elongating toward the red end of the light spectrum. This redshift was the smoking gun. It proved absolutely that the universe isn't just sitting there statically, it is continuously expanding outward from that very first point. To really grasp the next crucial clue, we kind of have to dust off our high school physics for a second. Hotter bodies emit shorter wavelengths. More energy equals faster moving particles, which gives you higher frequency, shorter waves. But what happens when that heat source expands over billions and billions of years? Well, as the universe expanded, it cooled off. So those initial highly energetic super short waves from the Big Bang, they stretched out immensely. And that brings us to 1965 and an absolutely monumental discovery. American physicist Arno Penzias and Robert Wilson stumbled upon the cosmic microwave background, or CMB. This is basically an ancient, super faint glow of electromagnetic radiation that literally fills the entire universe. It dates all the way back to roughly 380,000 years after the Big Bang. You can think of the CMB as essentially a baby photo of the universe. It shows us exactly what it looked like just after it was born. But hold on, why did it take 380,000 years to snap that baby photo? Well, early on, the universe was so insanely hot that atoms couldn't even exist. It was just this glowing, opaque, thick soup, a plasma of electrons and nuclei bouncing around. But once the expanding universe cooled down to about 3,000 Kelvin, this massive shift happened called the recombination era. Electrons finally paired up with protons to make neutral atoms, and suddenly, the universe became transparent. Photons could finally travel freely across space, releasing that cosmic glow that Penzias and Wilson caught billions of years later. Chapter 5. The Invisible Ghost. Okay, so let's recap. We've tracked cosmic dust turning into planets. We've mapped out the expanding galaxies. We've even traced the oldest light in existence back to the dawn of time itself. But there is one massive, completely unresolved cliffhanger in this whole detective story. 27%. An astonishing 27% of our entire universe is totally unaccounted for by traditional observation. Despite all our fancy instruments, our giant telescopes, and all our math, more than a quarter of the cosmos is entirely invisible to us. Just not there. We call this invisible stuff dark matter, and it is a literal cosmic ghost. It doesn't emit, absorb, or reflect any light whatsoever. We only know this ghost is out there because of its massive gravitational footprints. We can literally see its gravitational pull dictating how fast entire galaxies rotate, keeping them from just flying apart into space. We even see it causing gravitational lensing, which is when the light from distant stars actually bends as it passes by these enormous, invisible clumps in the dark. So, as we wrap up this explainer, I want to leave you with this one lingering thought. We've unlocked the secrets of nebulas, we've tracked the Big Bang's expansion, and we've literally snapped the universe's baby pictures. But if a whopping 27% of our universe is just this invisible ghost silently shaping the cosmos in the dark, how much of reality are we actually interacting with? It really seems like our great cosmic detective story is far from over. Thanks for joining me on this one. Keep looking up and keep asking questions.